subscribe to our YouTube channel, Joy Learning TV.
Wherever you are listening to me from, it's a privilege to come your way on your favorite Joy Learning channel on the Junior High School Hour. My name is Sir Okwabi. You can call me Sam Oaks. Always promising with, exciting topics and strands in mathematics. I urge you to stay on and tell your friends that the lesson has begun and let them tune in on all social media handles, Joy Learning TV. Let them stay glued to it. It promises to be exciting. Well, today I want us to look at another interesting topic or strand in our lessons for mathematics. Okay, I describe it as mapping. You know of it, right? We learned about it when we were in Basic 7 by way of patterns and relations. Okay, so we want to cement our understanding and bring the conclusion of that episode in this lesson. Okay, so in the next few minutes, we want to be going through activities by way of our objectives to understand the idea of mapping. Okay, we looked at relations, we looked at patterns. We want to extend it into mappings. Okay, so for our Basic 8 learners or our Junior High School 2 learners, this is your thing to do. So when we understand the concept of mapping, we will use the concept we have derived, the understanding we have derived, to be able to find the rule for the mapping. Yes, indeed, mappings have rules. We'll find the rule for the mapping, and then in subsequent lessons, we shall move on and look at how we can find the images of objects as well as the inverse of mappings. Okay, but for today, let's end at the rules of mapping. So I ask a simple question. What is mapping? Okay, when we treated the concept of patterns and relations, we are able to establish that usually when you have a relation between one object and the other, we can look upon that relation to create a series. Okay, so when we create that series and we can tell what gave birth or gave rise to what in that series, we describe that kind of relation as a mapping. And so today, for the lesson of mapping, when we say domain or input, what does it mean? When we talk of codomain or an output, what does it mean? We can also talk about range. We can also talk about gradient. And like I've indicated, the rule of a mapping. So remember we said that every relation begins somewhere. Okay, so for instance, if I want to describe a relation of a family, so I will say that Eja Kwejo, who is the father, gave birth to maybe Ama. So then in that case, it means that the mapping originated from Eja Kwejo and it came to land on Ama. So it begins somewhere. Okay, so when we talk about the domain or the input can be used, simultaneously, or one can replace the other. Another word for domain is input. So when we talk about the domain, we talk about the mappings that begins the relation, or the set where the arrows begin. The set where the arrows begin. And we know of arrows in mapping. We know that in relations, arrows play a key role. It tells you where the thing came from and what has happened to it to get us to where we are. Okay, so the set where the arrows come from or where the arrows originate is what is described as the domain. And then where the arrows end, we indicated that that becomes our codomain. So sometimes we call that one an output. Okay, so in your computing lessons, you know, anytime we have input, we also will have output. Okay, so in between the input and then the output, there is a processing. Okay, so in between the domain and the codomain, or the input and then the output, there is an arrow. That arrow describes the rule. In other words, we are asking, what happened to this figure in the domain that it became that figure in the codomain? You understand that? So assuming I tell you 2 maps to 2, and then the next one I tell you 2 maps to 3. What happened to the first 2 that it gave birth to a 2? That thing that happened should be the same that is happening in the second relation that I gave. Okay? And those things that are happening is the rule for the mapping. And we are going to look at it into details and tell what the rule can be. We also know that there can be what we call a range, and that sometimes in a mapping relation, not all the members in the codomain have a correspondence from the domain. They all don't have correspondence from the domain. Some members in the domain will not map to them. Okay? So when we say the range, we are only referring to only those ones that had a correspondence from the, the domain. And I'm sure if you are a regular viewer of this channel, you will know that we have done extensive work on patterns and relations, and then we know what we are talking about now. So that is a range. Only the elements in the codomain that have a correspondence in the domain, okay, that gives us a range. And then we have the gradient. So anytime there is a line, so long as the line is not vertical or horizontal and it is slanting, it has a gradient. Okay, and as we find the processes that will lead to the rules of this mapping, one thing we would need is a gradient. And so these are the things that as we go ahead, we shall be seeing them in our lessons. Okay, so we reviewed the lesson, and then we said that a relation between 2 variables x and y is a set of ordered pairs. Okay, so in our earlier lessons, like I said, if you are a regular viewer, you know we have done so much on this one. If you are new here, don't worry. I'll present it in a way and manner that will, become easy to understand. Then you can follow us as we go ahead. Okay. So an ordered pair consists of the x and then the y values put together. In other words, the value from the domain and its corresponding value in the codomain, when we put it together in parentheses, it becomes what we call an ordered pair. So we can generate several ordered pairs. Okay. So a relation may be viewed as ordered pairs, or sometimes we can call them as a mapping. Okay. Sometimes you can create a table out of the relation. Sometimes we can create an equation out of the relation. Sometimes we can simply write the relation in sentences. Okay, so we are going to see examples of some of these things. So remember that the x values that we are going to be talking about here are the values as contained in the domain. In the first set, the set where the arrows begin, they are the x values. Okay, the first numbers in the ordered pairs are the x numbers. Consequently, the second values in the ordered pairs are the y values, or better still, the set of values where the arrows end they are our y values, or the values of the output as set already, or the values of the range, they are the values of y. So that the values of the domain and then the values of the inputs, they also will become the x values. Interesting. So a mapping is a relation. We have established that it's a relation, okay, in which a member in the domain, so in a mapping, every time we have members in the domain, and for every member in the domain, every member in the set X, every member from the set of the inputs, that's the set where the arrows start or begin, map onto one and only one member in the codomain or in the output. Okay, some relations are not mappings. So what will make a relation a mapping is that every member in the domain must have a correspondence in the codomain. It must have mapped onto another member in the codomain. Okay? And so we'll see, giving some examples, which of them will be a mapping and which of them will be a relation. So usually it is often used to describe the set of ordered pairs. So when I pick the x value here, its corresponding y values, I put them in parentheses, is an ordered pair. So we're gonna have several ordered pairs for a mapping. Okay, great, interesting. So look at these examples of mappings. Okay, so we have these ones, the input and then the output. The input, that's where the arrows are starting, the one to the left, okay, in this diagram, the one to the left, and then the one to the right as output. It means that, for instance, 10 generated 15, or 10 gave birth to 15, or technically we say 10 maps to 15. 10 maps to 15. So that we can say that 20 maps to 45, 30 maps to 25, 40 maps to 35. That way. Okay. And so those to the left are the input or the domain. Those to the right are the output or the codomain. And as it is there, the members of the codomain are the same members of the range because all of them are mapped to. So like I said, sometimes you can have a codomain where not all the members in the codomain have been mapped to. And so in that case, only those that have been mapped to will form the range. Okay. Then we look at the second example. We see that we have a W mapping to D. So the first set has been described as a W, which is a domain. And then the codomain has been described as D. Okay. So great. So we can see that every member in the domain has a member mapped onto the codomain, or a member in the codomain. Okay. So one is a relation, one is a mapping. Okay. So if the mapping, or if in the relation, every member maps onto one and only one member in the codomain, then we describe it as a mapping. Okay. So in which ways can we describe mappings? I'm going to present to you 4 of the ways. We can present mappings by using the mapping diagram, like the one we just saw. Okay, this one. That's a mapping diagram. Once you see it clearly, you can know what is going on. Okay, it will speak volumes about itself. So we can present mappings by use of mapping diagrams. Okay, we can present mappings by a set of ordered pairs. Okay, a set of ordered pairs. We are going to be looking at examples of each of these ones. We can present mappings using algebraic relations. Okay, And then we can present mappings by the use of graphs. By the use of graphs. And so for mappings that is presented in the diagram form or in the mapping diagram form, this is how it will look like. So as we have seen, you will have the first set. In this one is described as set A, okay, which is the domain or the input or the X values, okay. And then we can have the second set. In this case is described as set B, which we refer to as the codomain or the output or the Y values. So you can see every member in the set A or the domain here, every member in the domain has been mapped to one and only one member in the codomain. So we have represented a mapping using a mapping diagram. So this is how it is. Okay, great, wonderful. Let's look at the second way of representing a mapping by use of ordered pairs. Okay, so the ordered pairs, as we are seeing, we see the first ordered pair 0, 2. What does it mean? It means that 0 mapped onto 2. If we were to present it using, mapping diagrams, okay. Then the second pair 3, 4. What it means is that 3 also mapped to 4. If we were to present it in mapping diagrams, okay. And then -3, -2, same way. It means in the domain it was -3, in the codomain it was mapping onto -2. That's what it means. So if I present to you an ordered pair, there is an understanding. Okay, we know where it came from. It tells us that the first values are the X values, the second values are the Y values. Okay, so that's a way of representing mapping by way of ordered pairs. And then we could also have represented in algebraic relations. Okay, so I can ask you, draw the mapping of y equals 2x. Yes, we can do that. Y equals 2x. So if x is 1, y will be 2. If x is 2, y will be 4. If x is 5, y will be 10. Okay, because the value of y is twice that of the value of x. So we can generate a whole data out of this relation. And that data that we can generate can be used to form the mapping, either using a diagram or any other way. Okay, we can even form a table out of this. So in the table, the first column will be x, the second column will be y. And I'll present to you some values of x and some values and their corresponding values of y in the table. Okay, so we have seen this being done in several aspects. Okay, so that's the way we show diagrams, mappings by way of algebraic relations. Then, as said, we could also show mappings using graphs, by way of graphs. And like we can see, we have two sets of graphs on the screen. We have a linear graph to the right. Okay, a linear graph to the right. That means that it was gotten from a linear relation. Like an example, the one we just saw in the algebraic expression, algebraic relation, y equals 2x. A relation like this will produce a linear graph like the one shown on the graph to the right, to my right. Okay. Then we can also have a quadratic graph. A quadratic graph like the one shown to my left or shown on my left. Okay, so when it's a quadratic graph, it will look that way. But each of them came from a certain mapping. For every value of x that we see in each of them, it has a corresponding value of y. Okay, so we can do all of this and show how the mapping will look like for each of them. And of course, we can even use tables, like I have indicated. I can use a table to describe a mapping where I'll see the values of x and the values of y, or the values of x and then the values of y. Okay, and of course, they are corresponding because there is a rule. There's always a rule connecting the x to the y, so that if x is a certain number, it has to generate a certain number for y. Okay, so that is a rule for the mapping. Good. Then we can also talk about types of mappings, or sometimes types of relations. So when we look at the first one, we have what we call one-to-one mapping. One-to-one mapping. Look at the name, one-to-one. One-to-one. One member in the domain corresponds to or maps to one member in the codomain. One member from X maps to one member in Y. One member from the input has only one member in the output. Okay, one to one. Okay, like our popular saying, one district, one factory. All right, one constituency, $1 million. Something like that. So it's 1 to 1. So when you have a relation like that, it is called a one-to-one mapping. So you can see that in this diagram, each member in the X has just one member in the Y, or it is mapped to only one member in the Y. So if you study it carefully, you will see that that is how it is showing there. So 1 maps to 5, 2 maps to 10, 3 maps to 15, 4 maps to 20, 5 maps to 25. Okay? So that's it. So we can have that one. And then the second type of mapping we want to talk about is the one-to-many relation. One-to-many relation. That one is a relation, it's not a mapping. I told you, for it to be a mapping, one member in the domain must map to only one member in the codomain. Okay, so this one is a relation. So you can see, for instance, in the domain, we have a member like A. Okay, and in the A, it is mapping onto I in the range. At the same time, it is mapping onto I in the range. So only one of them has two partners or two corresponding members in the codomain or in the range. You get that? So that's why we call it one-to-many. But don't call it one-to-many mapping. It is one-to-many relation. Okay, so that's the second one. Then the third one, we have the many-to-one mapping. Many-to-one mapping. So I can have a mapping in which all the members or more than one member in the domain maps to just one member in the codomain. Like what it's saying. Okay, 1 is going to 4, 2 is also going to 4, 3 is also going to 4. Okay, and there's a reason to that. The reason will be based upon the rule that connected each of them. And we are going to be looking at how to determine some of these rules. And then the last relation, we have the many-to-many relation. Many-to-many. So you can see that over here, we have certain digits or certain numbers in the domain or in the set A, many of them, or better still, let's say more than one of them. That means sometimes 2. Going to many other relations in set B. Okay, going to many other relations in set B. For instance, if you watch 3 and 4 in the set A, 3 and 4 in set A, 3 is going to 3, 4 is going to 2. Okay, so many of them, and they are also going to many partners in the codomain or in the output. All right, so that's a many-to-many relation. Okay, Now, we have understood the concept of mapping. Let's see what we can do to be able to determine the rule for the mapping. Okay, so we have said that every mapping is connected by a rule. Between the input and the output, there is a processing. Same way, between the input and the output, there is a rule. Okay, what is making the output to be what it is? Okay, and that is what we call the rule for the mapping, or the formula for the mapping. All right. The rule of a mapping, so we say, is the mathematical relation or the mathematical equation that connects the elements in the domain and the elements in the codomain. The mathematical relation or the mathematical equation that will connect the elements in the domain to the elements in the codomain. And once we mention equation, then you know that if one of them goes wrong, it won't hold again. Okay, it has to be true. It has to be true. So there's a reason why every member in the domain has that particular member being mapped onto in the codomain. And it is because of the rule or the mathematical relation or equation that connects the two numbers involved. So for instance, if I tell you that x maps to y, there's a rule that will make x have a certain value of y. So if I give you, for instance, 2, and I tell you it maps to 3, then if I give you 3, that should map to maybe 4, then that is developed out of a certain rule. So that next time, if I give you 4, you should be able to tell me what the 4 should give us. Okay, which, judging from here, is more likely to be 5. And if I give you a 6, you should be able to tell me what this 6 will generate. It should give me 7. Okay, so how you are coming by this, your answers, the 7, the 5, the 4, the 3, is what we call the rule for the mapping. How did you get it? Maybe you will tell me you added 1 to the x value. So x plus 1. So that's the rule. That's the mathematical relation or equation that connected the values of x, which is the first values, to the values of y, which is the second value. I want to believe that you are following. Remember, this is Joy Learning. We want to make sure that everything we present to you is done in the best possible form. Okay, so please take your time and go through the lesson with us. And if perchance you have a challenge with something being done, whether this one or any other episode, any other lesson, in any field and at any level, feel free and then come and put up that challenge, that question to us at Joy Learning TV on Facebook and on YouTube, and we'll address them for you. That's why we are here. We are here to make sure that we keep learning. Okay, so let's move on. If there are no challenges, we can move on. A mapping may be linear, like we have said. We can have a linear mapping. That means it will generate into a linear graph. Okay, or it can also be non-linear. That means it's not linear. It's not on a straight line. If it plots the graph of the ordered pairs, it will not be on the straight line. That means it's non-linear, not on a straight line. So, like we showed earlier on, I told you that showing relations by way of graphs, it can be a straight line graph or it can be a quadratic graph. In either way, if you want to find the rule for that mapping, there are two ways we can go about it. We can use the method of gradient or the gradient method, and we can also use the inspection method. And over here, I'm going to be leading you through each of these two processes to be able to know how to use all of them. Okay, so let's begin with the gradient method. Look at the name, gradient method. Okay, gradient. And as we have seen in our vocabulary, what gradient means, it simply means the slope of a line. So in using gradient method, it means you are going to be using the slope of a line, how slopey the line is. Okay, so we can use this method and apply them to only linear mapping types that are linear. Okay, they should be linear. Of course, it's gradient, so it should be a line that is sloping. It should be a straight line. It should be a straight line because we said we are going to use a linear mapping type, or we are going to use a gradient. We are going to use a gradient method to find it. So since it's a gradient method, and we are going to make use of a gradient, it means that it should be a straight line so that we'll be able to find the gradient. Okay, so to be able to determine whether a mapping is linear type or not, there's a way to go about it. And how do we do it? We just have to compare sometimes the gradient of two different pairs, at least two different pairs, ordered pairs. Okay, ordered pairs. We'll compare the two gradients of some different ordered pairs in the relation. And if the two gradients we find are equal or are the same, it tells us that that graph is a linear graph. That mapping is a linear mapping. Otherwise, it is nonlinear. Or a simple way to analyze it is for you to take the constant differences between the y values. So you take the mapping, you look at the y values in the mapping and find the differences from one y value to the next in succession. Okay, so if the differences from any of them are the same, any two of them or all of them remain the same, constant differences between the y values from one y value to the next, and then another set you find a difference, another set of y values you find a difference, and they are the same, it is an indication that the mapping is a linear mapping. Yes, it is. Otherwise, it is non-linear. So you have to first of all determine whether they have the same gradients or the same constant difference in their y values. If they have, then you are good to go. You can use the gradient method. Other than that, you have to use the inspection method. Yes, as a matter of, compulsion. So then, that's when we use the inspection method. Okay, when the equation or the mapping is not linear, then you are left with no choice. You have to use the inspection method. However, we still can use the inspection method to find the rules for linear graphs. Okay, we can use the inspection method to find it for both linear and not linear. But as for the linear ones, as for the gradient method, that one, the mapping has to be linear. If you want to use the gradient method, the mapping has to be linear. But as for the inspection method, we can apply it to both linear mappings or relations as well as non-linear mappings or relations. Okay, so that's great. So let's see how we are going to do it. So the inspection method is a way trying to find out using the try and error method. You try this and work, you think through it, you look at it, you ask yourself the salient questions: what happened to this to result into this? What happened to this to result into this? What happened to this to result into this? You ask yourself those questions, and then when you are able to generate a certain pattern, you are able to see the rule, and then that's it. You'll be good to go. Okay, that's great. So now we want to begin with some activities, and I'm asking you to find a rule for this mapping. So I have a mapping presented to you. X values are there, Y values are there. So 0, 1, 2, 3, 4 are the X values. In other words, the members of the domain are 0, 1, 2, 3, 4. Then the Y values or the members of the codomain are 0, 1, 4, 9, 16. So you can see it. 0 maps to 0, 1 maps to 1, 2 maps to 4, 3 maps to 9, 4 maps to 16. That's the question. So let's look at it and see. We want to begin using the inspection method. And why do you agree that we should use the inspection method? Like I said, we have to first determine whether or not the mapping is a linear or a non-linear mapping. Okay, so when we check from the data, what is the difference between 1 and 0? It will give us 1. Okay, what is the difference between 4 and 1? That's 3. Already we see differences in the differences. You see that? We see differences in the differences. Great. What's the difference between 9 and 4? Is 5. Clearly you can see from here it's not having a constant difference. Okay, the differences are different. Interesting statement. Okay, so indeed it will tell you that this is not linear. It's not linear at all. It is a non-linear mapping because the differences between the y values are not constant. The first one is 1, is 3, is 5, and even this one is also different, 7. Okay, for the mapping to be linear, these differences should be the same. It should have been the same. And if they are, there is a sure way of knowing that it's a linear mapping. Then you can use your gradient method to go about it. Otherwise, we are only left with the inspection method. So all we have to do is to study the mapping carefully with tact and see. Look at it. 0 maps to 0. Oh, really? Okay. 1 maps to 1. What about 2? 2 maps to 4. Ask yourself, what did they do to the 0 that its output became 0? What did they do to the 1 that its output became 1? What they have done in these two scenarios is the same thing they should have done to the 2 for its output to be 4. And the same thing they should have done to the 3 for its output to be 9. And the 4 for it to be 16. Look at it. Think through it. Okay? Within the next few seconds, think through it. Can you suggest something? What are they doing to the values of x to get their corresponding values of y? Can you suggest something? Okay. Well, if you are suggesting something, that's great. Okay, but can't you see that, for instance, the 4 in the domain, they squared it, 4 squared, meaning 4 times 4 is 16, right? Now the 3, they squared it, 3 times 3 is 9. Have you seen a certain pattern? Then the 2, they squared it, 2 squared, meaning 2 times 2 is 4. I mean, is it working? Yes, it is. Then the 1, they squared it, 1 squared, 1 times 1 is 1. Then 0 squared, 0 times 0 is 0. I mean, have you seen that? So this is what we do in an inspection method. We look at it, we analyze it, we think through it, ask ourselves, what did they do to the x to get a y? What did they do to the x to get a y? What did they do to the x to get a y? You will see that what they did in the first instance is the same thing they did in the second instance, the same thing they did in the third instance, and voila, you will get it right. And so in this one, we can clearly see that the rule for the mapping is that for us to get y, we square the x values. So y maps to x squared. We square the x values, and that gives us the values of y. So y maps to x squared. Okay? No stress at all. You will inspect. No working goes into it. You just inspect, and then you get it right. Okay, so that's it. The rule for this mapping, y maps to x squared. In some books, you will see it written x maps to x squared. Well, it's the same. Okay, it's the same. Sometimes here is given as x, okay, or y. It's the same. But for this lesson, we want to keep it at y or as y. Okay, that's great. That's great. That's great. Then we have the second mapping. What is the rule for the mapping below? Okay, so I present to you with the mapping. X maps to y, and the values of x are 1, 2, 3, 4, 5. The values of y, 8, 10, 12, 14, 16. Okay, so which method would you want to use? Okay, let's try and check the form of mapping that this one is. Is it a linear mapping or is it a non-linear mapping? So how do we check it? I gave you an easy way out, right? Look for the differences between their y values in succession. So what's the difference between 10 and 8? Is 2. That means the difference. Subtract, right? 10 minus 8 is 2. What's the difference between 12 and 10? Is 2. Okay? Are you getting something? Yes. What's the difference between 14 and 12? Is 2. Constant differences. This is what I talked about. Constant differences. The difference between 16 and 14 is 2. The differences are the same. Constant differences. This tells you that this mapping is a linear mapping. In fact, this constant differences is a gradient. Okay? Is a gradient of the line. The gradient of the line is 2. So with this, we know that it's a linear graph, meaning we have the option to choose whether to use the inspection method or to use the gradient method. Okay, don't forget that as for linear mappings, we can use both of them. Okay, it is the inspection method. As for the gradient method, we can apply it to both forms of mappings. It is the inspection method that we can only do it on the non-linear mappings. Okay, so that's done. Because we have seen one method or one example using the inspection method, let's apply the gradient method to this one. Okay, so quickly we'll find a gradient. That's why we call it gradient method. We'll find a gradient of the mapping or of the line. And like I have said, the constant differences is a gradient, meaning the gradient is going to be 2. But of course, you can't just start and say gradient is 2. You have to show. Mathematics, we have to show how we get gradients. Okay, so that you can earn all the marks. So we do it and we write the ordered pairs so that we can clearly see how the gradients are obtained. So these are the ordered pairs: x and y, 1 and 8, 2 and 10, 3 and 12, 4 and 14, 5 and 16. These are the ordered pairs. So finding the gradient, I'll choose 2 of the pairs, okay, and use them to find the gradient. So I'm going to take 1 and 8 as a pair, as one pair, and then the other pair 4 and 14. So it means that I'm going to have my x1, y1, x2, y2, gradient of the line, okay, change in y divided by change in x. So change in the y values divided by the change in the x values. Okay, so it means that I'll get 14, which is the second y value, minus 8, which is the first y value, divided by the 4, which is the second x value in the pairs that I chose. Okay, minus 1, which is the second x value in the pair that I chose, the 2 pairs that I chose. Okay, so 14 minus 8 gives me 6, 4 minus 1 gives me 3. So I get 6 divided by 3, and of course that's 2. Okay, so clearly we have seen that the gradient is 2. Okay, we said it, but you need to show how you got it. All right, so when you do the first one, for you to be certain, you need to do for a different set of pairs. Okay, and see whether you will get the same gradient like we did. when we're looking at whether the differences are the same, we didn't do for only one, we did for all of them. Okay, by here, 2 is enough. When you do for 2 different sets of pairs, and then you find their gradients and it's the same, it's okay. So I take another pair, another 2 sets of pairs. Okay, then I take 3 and 12, and then 5 and 16. Okay, so same way, gradient, change in y over change in x. So that gives me 16 minus 12, okay, divided by 5 minus 3. 16 minus 12 is 4, 5 minus 3 is 2. 4 divided by 2 is 2, okay? So in the first gradient, I got 2. In the second gradient again, I got 2. I'm good to go. The gradients are the same. It's okay for me. Now that I know the gradients are the same, I'll choose one of them and then choose one other pair to help me do it. So now I can confidently say that I have a constant gradient because my first gradient, which I call M1, okay, which is this one, is equal to my second gradient, which I'm calling M2, which is this one. Okay, so hence it's a linear mapping. Okay, so I've established that it's a linear mapping. Okay, so remember, you could have established this in your head, but for it to go on the paper and earn all the marks, you will need to go through this. Okay, so we have gone through it and we've seen the gradient that we are getting. Now, let's see how to get the rule for the mapping. All right, so for the rule for the mapping, we have the ordered pairs xy 1, 8, 0, 2, 10, 3, 12, 4, 14, 5, 16. That's it, right? I know my gradient is 2. Okay, so knowing that my gradient is 2, I'll take one of the pairs, which is xy. Okay, remember the equation of a line is y equals mx plus c, isn't it? Okay, this equation of a line can also be said to be the rule of this mapping. Okay, what is a m? M is a gradient, right? C is a y-intercept. Okay, so if in the rule there's a certain constant, that's for the C, and then the x and then y represent their usual connotations. Okay, so if I take x and y as a pair and another pair 2 and 10, and as if I'm trying to find a gradient for them again, okay, that same way will end me at this equation that I've done here. Okay, so it means that taking x and y as one pair and the second pair 2 and 10, that gives me the gradient of that pair as 10 minus y, right? Divided by 2 minus x. Okay, that's the gradient. Okay, as if I'm finding a third gradient. Okay, but remember, I have found 2 gradients already. Okay, so finding a third gradient, whatever I got in my earlier gradients should be the same, okay, to the next or the new one, the third one. Okay, and if that is true, then it means that this relation can be equated. Okay, my first gradient should be the same as my second gradient, and it should be the same as the third that I'm trying to find. Okay, so in the first and second gradient, I got 2. And if they should be the same, then it should be equal to the third gradient that I'm trying to find now. Okay, so that gives me 10 minus y divided by 2 minus x. I couldn't simplify that because of the way it is. 10 minus y cannot be simplified. 2 minus s cannot be simplified. But I can equate them because they are all gradients. You get it? Right. I can equate them. So my first gradient, my first and second gradient, which all gave me 2, should be the same as my third gradient. So I'm just equating the expression for the third gradient to the values of my first and second gradient, which is 2. Then it becomes an equation for me to handle or to simplify. And so I will cross multiply, okay? I'll cross multiply. So let me make things clearer, okay, so that you can get it now. Okay, great. So I cross multiply. So the 2 at my right hand side multiplies the denominator, and then the numerator stands alone. It has nothing to multiply with. That gives me 2 into bracket 2 minus x, okay, equals 10 minus y. It becomes a simple equation I can easily simplify. Okay, so I expand the bracket, or I distribute the left hand side. That gives me 4 minus 2x. Okay, of course, it will be equal to 10 minus y. Okay, then from there, I arrange it so that my y will stand alone as a subject. Okay, so when that is done, it means that I bring my y from the from the right to the left. That becomes, or it changes from negative y to positive y. Okay, and all others go to the right or remain at the right. So then the 2x, which is here as negative, okay, it will move in the next to the right and become positive 2x. The 10 is already at the right, it remains there, so no sign changes. Okay, then the 4 is positive, it goes to the right and it becomes a negative. So I end up getting y equals 2x plus 10 minus 4. Okay. And then I can simplify the 10 minus 4 to give me 6. Okay. So that gives me y equals 2x plus 6. Y equals 2x plus 6. And therefore I can conclude that the rule for the mapping is y equals 2x plus 6. You get that? So look at it again. If you consider it, the y values are gotten how? By multiplying the values of x by 2 and adding 6 to the product. Okay, so for instance, when x was 1, we multiply the 1 by 2, okay, that gives us 2, and then we add 6, that gives us 8. That is why the y value in that one is 8. And we could have done this by way of inspection. Okay, that's great. That's great. Now, we have done enough. It is time for you to practice something. As usual, I'm going to give you a time of 60 seconds to make an attempt at this one. I'm asking, what is the rule for the mapping below? Okay, so take your time. Maybe you want to use inspection. It is your decision. But within 1 minute, look at it for me. That's 60 seconds already gone. And I want to believe that you have some answer waiting for me. Well, I want us to compare what you are having with what we expected. Okay, so I got my root to be 2x plus 3. I don't know what you got, but at least we can test this to see using the inspection method. So for the values of x, they are 0, 1, 2, 3, and 4. So if I pick a value of x to be 0, I am saying that to get the y value, multiply the x value by 2. So 2 times 0. And that will give me 0. Okay. Then add the product, add 3 to the product. So the 0 I got plus 3. And that should give me 3. So it has worked here. Okay. Then if I pick for 1, 2 times x, so 2 times 1, that will give me 2. And I add 3 to the 2, that will give me 5. So it has worked. I do this for all of them. If it works, fine. I'm done. Okay. So for x is equal to 2, x equals 2, it means we are going to have y to be equal to 2 times 2, giving us 4, plus 3, 7. It has worked. For when x is 3, it means we are going to have y to be 2 times 3, which is 6, plus 3, which is 9. It has worked. When x is 4, 2 times 4, that's 8, plus a 3, 11. It has worked. I don't know which method you used. You could have used the gradient method. You could have used the inspection method. But I went for the inspection method. And my rule is y maps to 2x plus 3. And that is the answer I expected. And if you got that, then I'm proud of you. And I'm happy you did it and you got it. If you did not get that, don't worry. I'm still proud of you for the fact that you did it, you attempted it, and then you got it. I'm happy. And congratulations for at least making an attempt at the question. So great. That is very interesting enough. And so this is a time where I would need you to look at this question. What is the rule for the mapping? Below, to be taken as an assignment. Get it done, and then you will get the response. To me, I will give you your feedback. So what you will do is to take a snapshot of it if you have any device. If you don't have any device, quickly write it out, write the mapping out, and remember the simple task is that you are finding the rule. X maps to y, 1 maps to 0, 2 maps to a quarter, 3 maps to half, 4 maps to 3/4 or 3/4, 5 maps to 1. You can do me the honors of finding the rule for this mapping. And when you are done, visit me on Facebook or YouTube, Joy Learning TV, and post your response to me, and I'll be glad you interacted with me. I'm also willing, more than willing, to interact with you. Well, it's always exciting if I come your way and we are able to complete a season or a section or a strand or a topic. Thank you very much for the time you have spent with us. It's worth it. And may you keep learning. This is Joy Learning. I'll come your way again. Till then, my name remains Samuel Okwabi. Call me Samux. Bye-bye.
YouTube channel, Joy Learning TV.